Now, I know we've done some work with trig integrals, but we're going to spend some time working on just powers of sine and cosine and powers of secant and tangent, which is easily translated into cosecant and cotangent. So let's go ahead and get started. We'll start with powers of sine and cosine. Anytime you have an odd power, you can always isolate that one, stick it with the dx, and make that the du for your u substitution. So let's do an example, show you what I mean. You're going to use the Pythagorean identity over and over again in this section. So we have cosine cubed of x dx. You're going to have to use those powers of rules of exponents. So we know that cosine cubed is equal to cosine squared times cosine. Now, I want this to be my du. So I need to rewrite cosine squared as something with sines in it. And thanks to the Pythagorean identity, I can rewrite this as 1 minus cosine sine squared of x times cosine of x dx. Now, I'll let u be equal to sine of x, then du is cosine x dx. So what I really have here is the integral of 1 minus u squared du. And that one's easy peasy because we have integral of 1 would just be u, and then add 1 to the exponent, divide by the new exponent, and never, ever, no, not ever forget to add c. So u is actually sine of x minus sine cubed of x plus c, and I forgot to put that over 3, but I caught myself, and there's the pretty answer. Works the same if we already have some sines and cosines mixed up together. As long as one of your trig functions, sine or cosine, has an odd exponent, you're good to go because sine and cosine are derivatives of one another. So let's look at example 2. We have the integral of sine to the 5th. And because this is going to take a lot of writing, I'm going to go ahead and write that as sine to the 4th of x times cosine squared of x. And I'm going to put this sine of x over with dx. So we isolate one of the trig functions and put it with the dx, and that's going to take the place of our du. This one's going to be a little trickier because the derivative of cosine is equal to negative sine. So I want this to end up being negative of du. I'm going to let u be equal to cosine. That means I need nothing but cosines over here. But I know the rules of exponents. I know that sine to the 4th is just sine squared squared times cosine of x times sine of x dx. And I'm friends with Pythagoras, so I know that this is equal to 1 minus cosine squared of x times cosine squared of x times sine of x dx. Now I'm ready to let u be equal to cosine of x, then du is equal to negative sine of x dx. So what I have here is negative sine of u. So this would be the integral of 1 minus u squared times u squared, squared. I almost lost a squared, then I would have had the wrong answer, times du. Now it's algebra time, because I can't do any other substituting in here. I'm just going to have to expand it all out. So 1 minus u squared would be 1 minus 2u squareds plus u to the 4th power. Still have that u squared sitting outside of the parentheses. And now I'll distribute, so I have u squared minus 2u to the 4th plus u to the 6th. And I need a negative out here because this was negative du. And let's make that look neater. Equals negative. I just pulled that negative and put it out front. So everybody gets a brand new sign, add 1 to the exponent, divide by the new exponent. So negative u cubed over 3 plus 2u to the 5th over 5 minus u to the 7th over 7 plus a constant. And this is actually cosine, so cosine cubed over 3 minus 2 cosine to the 5th over 5 minus cosine to the 7th over 7 plus a constant. And let's look at the pretty solution, make sure I didn't lose anything along the way. And it looks like we did good. Now I'm going to take a break and go to a new page. Examples 1 and 2 require the Pythagorean identity because we had an odd exponent on one of our trig functions that we could pull off to be our du and use u substitution. This time we only have an even exponent on our trig function. So we're going to have to use the half angle identities. And I'm going to write them down. Sine squared of x is equal to 1/2 of 1 minus cosine of 2x. And yes, you do need to memorize that. Cosine squared of x is 1/2 of 1 plus cosine of 2x. You do need to memorize those. You also need to memorize the sine of 2x is 2 cosine x sine x, that one double angle formula. If you need one of the other ones, you can always get them from looking at cosine of 2x if you need the cosine. So let's rewrite sine squared using this half angle identity. Integral from 0 to pi, and I'll replace sine squared with 1/2 1 minus cosine 2x dx. Well, that's easy. I can pull 1/2 out front. Integral from 0 to pi 1 minus cosine 2x. You could do u substituting if you really wanted to, but we've done it a lot with just cosine of a number times x. You should know by now that the antiderivative of that would just be x minus sine of 2x over 2, because the antiderivative of cosine is just sine, so it keeps the minus sign. And then when you take a derivative, you multiply by the number sitting next to the variable. When you anti-differentiate or integrate, you divide by that number. And now we'll evaluate this from 0 to pi. So I have 1/2 pi minus sine of 2 pi over 2 minus 0 minus sine of 0. That's all 0. That's all 0. So it's really just pi over 2. Not bad. Let's check our answer. Oh, look at that. Exactly right. Okay, example 4. Now we've got sine to the 4th power. Go ahead and pause and see what progress you can make. Try doing this one on your own. You're going to use the same half angle formula, and you're going to have to square it. So to the 4th power is just squared squared. So sine squared of x squared. Don't know why I have a 0 at the bottom there. This is an indefinite integral. So I have 1/2 of 1 minus cosine of 2x squared. 1/2 squared is 1/4. I'll pull that out front. And then I have 1 minus 2 cosine of 2x plus cosine squared of 2x. Now I have another trig function with an even exponent on it. I'm glad I wrote down this other half angle formula up here. So this 1/4 integral of 1 minus 2 cosine 2x plus 1/2 of 1 plus cosine of 4x. So we can do some arithmetic. We have 1/4 integral 1 minus 2 cosine 2x plus 1/2 plus 1/2 cosine of 4x. Then I have 1 plus 1/2. It's 3/2. So I'm going to go ahead and start integrating because I'm running out of room. So 3/2 x. Then minus antiderivative of cosine of 2x would be minus 2 sine 2x, but I have to divide by 2 because of the 2 sitting right there. I took care of that because I combined it with the 1. And now I have 1/2 sine of 4x over 4 plus a constant. And let's do some distributing here. So I end up with 3/8 of x. That cancels with that. So minus sine of 2x over 4 plus sine of 4x over 2 times 4 is 8 times 4 over 32 plus a constant. Hopefully I made it through all of that correctly, and yay, I did make it through all of that correctly. Yay me. So, I give you a strategy, and I'm going to kind of simplify it. We have here A and B. These are what happen when you have an odd exponent. So, either sine or cosine has an odd exponent. Odd exponent. If that's the case, then you isolate and combine with dx to be du. U is equal to the other trig function. So isolate that function, combine it with the dx, that'll be your du, and then u is your other trig function. And you may need to have to throw a minus sign in there, so be careful with your signs. If all exponents are even, then we use half-angle identities. And I'll write them down again just to help you memorize them. Sine of 2x, they always start with a half and 1. Sine gets the minus sign. Cosine gets the plus sign. Easy enough. And here's all the pretty ones. And I have sine of x, cosine x equals 1/2 sine of 2x. I usually remember it as sine of 2x is 2 sine x cosine x, which is the same darn thing. So pause here, do practice number 1. We'll come back together and compare answers. Let's look over practice number 1. We have the integral, and I went ahead and wrote it as sine to the 4th times sine, and I wrote sine to the 4th as sine squared squared. And then I replaced sine squared with 1 minus cosine squared. Thank you, Pythagoras. I squared it down here after I plugged the u's in, because then I didn't have to write as much. I'll let u be equal to cosine. Then du is negative sine, so I replaced that sine x with negative du. And then I updated my limits of integration. At this point, I could have gotten rid of the minus sign and evaluated from 0 to 1. Doesn't really matter. You end up with the same correct answer no matter what. You plug 0 in, you get 0 minus 0 cubed plus 0 to the 5th, which is 0. And then you plug 1 in. Zeros and 1s are the best to plug in. They're the easiest. You should end up with 8 over 15. And you can use your calculator for the arithmetic. Let's look at number 2. You can see this one has an even exponent, so we know we're going to need the half-angle identity. Not too bad. We just had to use our half-angle identity. Remember, whatever is in here gets doubled when you do the half-angle identity. And then you divide by whatever is sitting next to your variable in the cosine function. You divide sine by that, and then I just flipped it upside down, and then I figured out sine of 4 pi over 3. It has a 3 in the denominator, so it's square root of 3 over 2, and 4 pi over 3 lives in quadrant number 3, so sine would be negative, so it's negative square root of 3 over 2. I distributed and got an answer. Hopefully you got the same thing. Okay. Sines or tangents and secants will start out, and we're actually only going to do ones that we can use the Pythagorean identities for on these. So first, let's just review that Pythagorean identity. The one that everybody remembers, sine squared plus cosine squared equals 1. Divide everybody by cosine squared. Then we have sine over cosine is tangent squared. Cosine over cosine is 1, and 1 over cosine is secant. Now, I always just remember secant is bigger than tangent, so secant squared is tangent squared plus 1. That helps me to remember it. You're also going to need to know that tangent squared of x is secant squared of x minus 1. Tangent smaller, so subtract 1 from secant to get back to tangent. But these are the identities that you need. Now think about secant and tangent. Derivative with respect to x of tangent of x is secant squared. So if you have an even exponent on secant, you're going to pull off a secant squared, put it with the dx, and let u be equal to tangent. Remember, you always have two secants and a tangent. So if you're taking the derivative of secant, then you got to have another secant and tangent. So if you have an odd exponent on tangent, then you can isolate a secant and a tangent and let secant be equal to your u in u substitution. Let's do some examples. Tangent to the 6th, secant to the 4th. And let's see, I said I was going to isolate secant, so let's go ahead and do that. I have tangent to the 6th of x, secant squared times secant squared. This is going to be my du. And now you see I'm left with an even exponent on secant, and that way I can rewrite that as tangent squared plus 1. So this is the integral of tangent to the 6th times secant tangent squared plus 1. Yeah. And I could have put 1 plus tangent squared, but I didn't. Times secant squared of x dx. Now it's all ready to let u be equal to tangent. Du is secant squared. So what I really have here is u to the 6th power times u squared plus 1 du, which is u to the 8th plus u to the 6th du, which add 1 to the exponent, divide by the new exponent, add c, over 7 plus a constant. And there, I go through it in nice detail for you. Okay, this one, we do not have an even exponent on secant, but we have an odd exponent on tangent, so we can take one of those away from tangent and we'll be left with an even exponent on tangent, and we can rewrite that using our Pythagorean identities. So that's my goal for this one. Example 6. We have tangent to the 5th, so I'm going to write that as tangent to the 4th of x, and secant to the 6th of x, and now I have a tangent of x and a secant of x living there next to dx. That's going to be my du, and u is going to be equal to secant of x. But now I need to get everybody over here in terms of secants. So tangent to the 4th is tangent squared squared, so let's write that first. Tangent squared squared times secant to the 6th times tan x secant x dx. Haven't changed anything. I just rewrote that. Now I'll replace tangent squared of x with secant squared minus 1. Oops, left my C out. Now, u is equal to secant of x, so what I really have here is u squared minus 1 squared times u to the 6th power du. Well, I think we know how to square things by now. We've done it several times. We have u to the 4th minus inners and outers gives me 2u squared minus 1 6 du. I'm ready to distribute. So u to the 6th times u to the 4th. Laws of exponent says I just add those exponents. So it's u to the 10th minus 2u to the 8th minus u to the 6th du. Add, divide, and that should have been a plus because negative times negative is a positive. So u to the 7th over 7 plus a constant, and u is actually secant to the 11th minus 2 secant to the 9th plus secant to the 7th plus the constant because we don't want to lose a point. And there's our pretty answer. So, if the power of secant is even, then you isolate that and let u be equal to tangent. If the power on tangent is odd, then you're going to isolate a tangent and a secant with a dx and let u be equal to secant. If it doesn't fit either of those patterns, I won't give you a problem like that. So on test day, you only need to know how to do these two techniques. So, number 3, give this one a try, see what you can do with it, and we'll meet back and compare answers. Now this one doesn't really fit either of those patterns, does it? And I just told you I wouldn't make you do anything that didn't fit those patterns. But you're pretty savvy. You should notice that you could factor tangent squared out of there. And then after that, you see you have 1 plus tangent squared. Oh, you can replace that with secant squared. So this would be tangent squared of x times secant squared of x. Oh, there's du sitting there smiling at you. That makes this u squared. So the integral of u squared du equals u cubed over 3 plus a constant. So tangent cubed of x over 3 plus a constant. So that was a little tricksy. You didn't exactly use those strategies. This one, however, can definitely use those strategies because you see that we have an odd exponent on tangent, so we're going to isolate the tangent and the secant and then let u be equal to secant because our du will be the derivative of secant. So do that one and then we'll compare answers on that. This was almost exactly like example 6. And you'll start to see patterns in these as you do them. We let secant be equal to u. We pulled off a tangent and a secant. And you notice it doesn't matter whether secant has an even or an odd exponent in these examples because you're going to just end up leaving it alone and distributing that one through the other one. What's important is that you can pull off the one tangent and end up with an even exponent on tangent because all even exponents are really powers of x squared. So, easy enough. And you are welcome once you get to this part to go directly to your answer. You don't have to write the answer with u's in it and then write it with secants in it because I know you get tired of writing. Okay, for other cases, the guidelines are not as clear-cut. You may need to use a little ingenuity, so it may get a little tricky. Integral of tangent, you probably did this one back in Calc 1. Maybe you remember it, maybe you don't. Integral of tangent. Since we don't have it memorized as a rule, we would probably rewrite it as sine of x over cosine of x. Then we would let u be equal to cosine of x, du is equal to sine x dx, and we can go ahead and divide both sides by sine of x if you want to. And then when we do our substituting, we end up with sine of x sitting on top of u, du sitting on top of sine of x. So those things cancel and we're really, really happy. Or you just notice that you really had du sitting on top of u. And this is minus sine, so we would have a minus sitting out in front here. So this would be negative natural log of the absolute value of u, which is negative natural log of the absolute value of cosine. But remember the laws of exponents, or the laws of logarithms, excuse me. If you have a number sitting in front of the logarithm, it's really a cleverly disguised exponent because logarithms are indeed exponents. This is actually the natural log of the absolute value, didn't lose its absolute value, of cosine of x. So 1 over cosine of x, not inverse cosine, but 1 over cosine, which is secant. Memorize it. You'll be glad you did in the next section. Integral of tangent is the natural log of the absolute value of secant. And here's a pretty solution. Now, secant isn't quite so straightforward, but you do want to memorize this. So I'm going to go through and show you how to calculate it. I'm going to start just by writing it as, no, I'm not going to write it as 1 over cosine. I'm going to leave it as secant because we're going to multiply by 1 in a very strange way. Secant of x plus tangent of x over secant of x plus tangent of x. Okay, remember I said ingenuity. Yeah, this is ingenuity. So we have the integral of secant squared of x plus secant x tangent x living on top of secant of x plus tangent of x. I wouldn't have expected you to come up with this idea all on your own. It doesn't just jump out and say, do this. This is something that somebody figured out and we all just said, hey, good for you. We're going to use that. So let's let u be equal to this denominator. Then du would be equal to derivative of secant, which is secant x tangent x. Hey, that's right there. Plus the derivative of tangent, which is secant squared of x dx. And look at that. We just happen to have the integral of du over u yet again. Natural log, absolute value of u. So it's the natural log of the absolute value of secant of x plus tangent of x. Again, memorize that. You'll be glad you did in the next section. Okay, example 7. Tangent cubed. So we need to use some ingenuity here. Because it doesn't follow either of those rules, but it's something that you should be able to figure out how to do. Let's factor out a tangent of x, and we're left with 1 times tangent squared of x. Then we'll go back and use our Pythagorean identity again. And tangent squared is secant squared of x minus 1. Now I can distribute that tangent. So I have the integral of tangent of x times secant squared of x. And you could even divide it up into two different integrals if you really wanted to. Tangent x secant x dx minus tangent of x dx. Well, now I can let u be equal to the tangent of x, and du is secant squared of x dx. So this piece is the integral of u du, and then this one we just memorized. It would be minus integral of tangent is the natural log of the absolute value of the secant of x. So I end up with tangent squared over 2 minus the natural log of the absolute value of secant plus a constant. We got it. So I thought I was going to go ahead and get a head start on this one. I went ahead and divided it up into secant times secant squared. And then I got here and I got kind of stuck because I have secant of x times tangent squared of x, and I don't have an even exponent on secant, and I don't have an odd exponent on tangent, which I could do some manipulating and use integration by parts, but if I'm going to do that, I just as well look at secant cubed and do integration by parts, because secant cubed, again, is secant of x times secant squared of x. I could let u be equal to, let me get this out of the way, u could be equal to secant, then du is equal to secant x tangent x. dv could be equal to secant squared of x, which means v would be equal to tangent of x. So my integral that I started with here, secant cubed of x dx, would be equal to u times v minus the integral of v du. Still looking pretty ugly, isn't it? But let's do some identities here. We have secant x tangent x, and this is really secant times tangent squared. So it's secant of x tangent squared of x. But tangent squared is equal to secant squared minus 1. So this is secant x tangent x minus the integral of secant x times secant squared of x minus 1 dx. So this is secant x tangent x minus the integral of secant cubed of x minus, oops, don't lose my dx. Well, let's go ahead and leave it in one piece first, minus secant of x dx. So first I just distributed. So now we have secant of x times tangent of x minus the integral of secant cubed of x dx. I have minus minus, so plus the integral of secant of x dx. Oh, but I have secant cubed equals something minus secant cubed, so I can add that to both sides. This is loopy, integration by parts, Pythagorean identities, and we have to know the integral of secant. Holy cow, we're putting it all together. So 2 times the integral secant cubed of x dx would be equal to secant x tangent x plus the integral of secant, which is the natural log of the absolute value of secant of x plus tangent of x. So my integral of secant cubed of x is really 1/2 of secant of x tangent of x plus the natural log of secant of x plus tangent of x plus a constant. And yeah, it took me a while to get through that on here too, but we end up with the exact same thing. These I do not expect you to memorize. I expect you to recognize them, and then you have my permission to Google these formulas if you need them. So you are not expected to memorize them. Just know if you have sine of something times cosine of something, or sine times sine, or cosine times cosine, something like example 9, I expect you to be able to look up that formula and then use it. So I'll write this one down and we'll go through it together. So I wrote down my original integral, And then I looked up here and noticed it looked like sine times cosine. So my m was equal to 4 and my n was equal to 5. So I did half of sine of 4 minus 5x plus sine of 4 plus 5x, which is just 1/2 the integral of sine of negative x plus sine of 9x. And either you remember that even odd identities tell us that sine of negative x is the same thing as the negative sine of x, or you just let u be equal to the negative of x. Either way, you end up with the integral of sine is negative cosine, so you have negative cosine of negative x over negative 1. 1/2 is multiplied by all of this, minus cosine of 9x over 9 plus a constant. And you could simplify this because you have a minus on top and a minus on bottom, and cosine of minus x is the same thing as cosine of x, so really this is just 1/2 cosine of x minus cosine of 9x over 9 plus a constant. And let's see, oops. Yeah, I end up with the exact same thing. Alrighty. That's all the examples I have for you. Look at your lab. There's some practice problems in there for you to work on. You got this.